All right, so in this video, we are going to discuss electromagnetic radiation, which is emitted from, let's say, an arbitrary charge density and current density. Okay, so before we go on to that discussion, let me consider a very simple example of a so-called spherical electromagnetic wave. Okay, so we have already seen what are called plane electromagnetic waves, and those were plane waves because at a given instant of time, the surfaces over which the phases of the electric and magnetic field was constant, those surfaces were planes essentially. Okay, so that is the reason why those electromagnetic waves were called plane electromagnetic waves. But now we are going to discuss through an example, through perhaps one of the most simplest examples of what are called spherical electromagnetic waves. And that basically we will discuss through an example. Again, I'm not going into a more detailed discussion of this because a very detailed discussion would involve us to use the so-called spherical harmonics. And again, some of you in class may not be familiar with spherical harmonics yet. So basically, we'll stick to an example, and I hope the main idea or the concept will be more or less clear if we consider just one simple example. Okay, so this example that I have here is basically taken from a problem or an exercise in Griffiths. So you can look at that problem. And so here, as you can see, that I have written down electric and magnetic field here. And the electric field is pointing along the phi direction, whereas the magnetic field has a component along the r hat direction as well as along the theta hat direction. Okay. And you can check that this set of electric and magnetic fields solves the vacuum Maxwell equation without sources. Okay, so this is very similar to what happened for plane electromagnetic waves. We have seen that plane electromagnetic waves are solution to vacuum Maxwell's equation without sources. And so if you plug this into these equations, you will see that these equations are satisfied. And of course, you have to set omega equal to ck, as we also did for plane electromagnetic waves. Okay. So you will see that this is a solution to this vacuum Maxwell's equation, and that verification, that algebra, I leave as an exercise for you guys to do. Okay, but let's say you verify that this is a solution. Now, if we verify that this is a solution with this electric and magnetic field, we can compute the so-called Poynting vector, which you have encountered in our discussion about conservation of energy. So this Poynting vector essentially has the interpretation of energy current density. Okay, so if we take this Poynting vector and if we integrate it over a surface, let's say, okay, so let's say there's some surface over which we integrate it, this is going to give us the energy per unit time that is crossing this surface, or this is going to give us the power that is moving through this surface. Okay, and in this case, we are interested in computing that power. That is why we are computing the Poynting vector here, okay, for this particular solution. So if we compute the Poynting vector here, then basically you will see that there are many terms here. One term is proportional to r hat, and the other term is proportional to theta hat. And so you can again take the cross product between this electric and magnetic field, and you will find that this is the expression for the Poynting vector. Okay, if you just take the curl. Sorry, if you just take the cross product. So now if you take the Poynting vector and if you further take the time average of this Poynting vector, by which I mean you integrate the Poynting vector over time over one period of this. So basically this is this has a wave nature or oscillatory nature, this solution, because as you can see there's this omega t here. So so if you compute if you take the corresponding time period and integrate this s over one time period 0 to t and divide by the time period, then you get what is the time average over one time period for this solution, okay, for this spherical wave. So now, if you take if you see this quantity, you will find that all these terms, all these other terms that go as sine and cos, they vanish because of the time averaging. Only the term which is proportional to cos square, that is the term which gives you a factor of half, and upon time averaging, and that is the term which contributes to this time averaged Poynting vector. Okay, and because this term is along the r hat direction, so this time averaged Poynting vector is also pointing along the r hat direction. Now, so basically, there's one thing that I want you to appreciate, that there is another thing that is special about this term. Not only it survives time averaging, it is also the term with the lowest power of r in the denominator, because this is the only term, if you see among all these terms, this is the only term that goes as 1 over r squared. There's a r to the power 5 here, there's a r cube here, that cancels, and that gives you 1 over r squared. So basically, this time averaged Poynting vector also goes as 1 over r squared. Okay, so now, this fact is going to be absolutely crucial in our discussions, and therefore, let me try to emphasize this point, that the Poynting vector goes as 1 over r squared. Now, if we look back at the electric field and the magnetic field, we will see that the electric field and the magnetic field as well has terms of various powers of r in the denominator. And if we just consider the power of r in the denominator, which is the smallest, we consider the term in the electric and the magnetic field which has the smallest power of r in the denominator. So here this is going to be this term, and for the magnetic field this is going to be let's see, this term. Okay, so these are the two terms that have the smallest power of r in the denominator, and that small power is 1 over r. Okay, these are the two terms in the electric and magnetic fields that goes as 1 over r. So now, if we just focus on those terms that goes as 1 over r, so we'll find that the electric field for that term is along the phi hat direction, whereas the magnetic field is along the theta hat direction. They are mutually orthogonal to each other. And if we try to compute the Poynting vector just corresponding to these two terms, then we will see that this is the answer, where we have a cos square, and this is the same term as the term here which contributed to the time average. So if we just took these two 1 over r components, or 1 over r terms of the electric and magnetic field, and computed the Poynting vector, and took its time average, then as far as this time average thing is concerned, this is identical to the time average which we obtained by considering the full solution, or all the terms. Okay, so basically the 1 over r term in electric and magnetic field contributes a term in the Poynting vector that survives time averaging. Okay, so this is again something very interesting and to observe. So also these are the two terms which can give rise to this 1 over r square term in the Poynting vector, because the electric field goes as 1 over r and the magnetic field goes as 1 over r, so their product gives you a 1 over r square in the denominator. Okay, so this ensures that the Poynting vector is falls off as 1 over r if we consider 1 over r squared if we consider these two terms which goes as 1 over r, right, in the electric and magnetic field. Now, if we with this time averaged Poynting vector, if we try to compute the total power that is moving out through a surface of radius r, so basically, let's say here is the origin, I consider one spherical surface of radius r, and try to compute the total power that is moving through that surface centered at the origin, then we will basically have to perform this integral. Okay, so this integral, the area element on the area element on the spherical surface, this is given by this quantity here. It is of course pointed radially outwards. The Poynting vector, again, the time averaged quantity is pointing along the radially outward direction. And so if we now take a dot product, the r hat dot r hat is going to give you 1. But the most important thing is the r square coming from the area element will cancel the 1 over r square in the denominator of the Poynting vector. This cancellation is extremely important, and because of this cancellation, it is this term in the average power, that becomes independent of R. So this is independent, has, this result has no dependence on R. So it does not matter what is the radius of the surface that you are considering. No matter how large, the total power moving out from this surface is going to be constant. Okay, so of course the energy gets distributed over the whole sphere, and because it's a larger and larger sphere, the energy density kind of goes down. But so as you can see, the energy current density is going down, but still the integrated power over this surface, that remains constant, independent of R, if this goes as 1 over R squared. If this went as 1 over R cubed, for instance, or 1 over R to the 4, then this cancellation wouldn't have happened, and you would be left over with a, R to some power here, and that would tell us that the power goes on decreasing as we move further and further away. But this is not the case here. Here, the power remains constant over a surface of any radius. And this is precisely, therefore, these terms in the electric and magnetic field. Okay, these special terms in the electric and magnetic field, therefore, are very special in the sense that these terms carry amount of energy or power that is moving out from the origin, and it kind of carries this energy irrespective of the radius of the sphere. So it carries this energy and moves away. So these are, in some sense, a response is seen as electromagnetic radiation from a far, far distance, because the power is never going to decrease. Okay, the power, the integrated power or the total power through the surface, that is never going to decrease. And so these are the terms in the electric field that lives very, very, that is important even at distances far, far away from the origin. Okay, so presumably, as you can see, the electric and magnetic field, they are ill-behaved at the origin because of this R, they go as 1 over R. So presumably something is happening at the origin. There's some source or something that is giving rise to these waves. And these terms, this 1 over R terms in the electric and magnetic field is kind of leaving the charge density and moving away from that configuration and moving out as electromagnetic radiation. So, and the power in the electromagnetic radiation is this constant power that we have seen, or let's say if we are interested in one specific direction, then this is the amount of power that is moving, through one particular solid angle for theta and phi, that value. This is the particular power that is moving in a given direction. So far so good, but you see, this set of waves, here there's kr, right? Again, because this is kr, you can think of this kr as something like k vector dot r vector, where k vector is basically omega by c r hat. Okay, so you can think of this as the k pointing in the r hat direction. So basically this is the wave vector, and therefore this represents a traveling wave along the radial direction, right? This represents a traveling wave along the radial direction. And not only that, you see at a constant time, let's say time t equal to 0, the phase of the electric and magnetic field remains constant over a surface which is kr equal to constant. So this is basically r equal to constant surface. Okay, and this r equal to constant surfaces are essentially spheres. So these are therefore known as spherical waves. Okay, these are therefore referred to as spherical waves, and they have this kind of form. Their amplitude goes down as 1 over r, and they have the oscillatory behavior as is necessary for a wave, and it is also a propagating wave because of this particular combination here. Very good. Now, so as we have seen that the total power is therefore given by this, which is present in this electromagnetic wave, right? Just before we finish, there is one remark. I have already emphasized the importance of the cancellation of 1 over r squared and the r square factor coming from the area element of the sphere, so because these are the terms in the electric and magnetic fields, the 1 over r terms are the terms in the electric and magnetic fields which contribute to this radiation far, far away. Therefore, these kind of terms, which go as 1 over r in the electric and magnetic field, they are called the radiation fields. Okay, they are called the radiation fields, and here, this is another interesting remark. So you see that if I consider let's say this is the origin, and this solution is such that there is a propagating wave far, far away along this direction. So you see, if I consider a small area element here directed along one solid angle, then if the radius of this sphere is very, very large, then this little area element would essentially resemble that of a plane, right? This area element would resemble that of a plane, and therefore, from a distance far, far away, these spherical waves would kind of seem like, they can be well approximated by plane waves as well. Okay, so what is going on is essentially, of course, the phase is constant over the sphere, but a tiny element of the sphere, that's almost like a plane. So these are like plane wave. These are like plane waves, approximately plane waves, if looked at from a distance far, far away. Of course, you can say that it goes down as 1 over r, but let's say, you are at 1,000 kilometers and you study the wave for 1 more kilometer. So, the difference would be, 1 over 1,000 and compared to 1 over 1,001, that number is going to be that difference is going to be very small. So when the sphere is very large, then for considerable distances, this factor can be considered to be constant, and because this factor can be considered to be constant, therefore we can say that these are approximately plane waves. Okay, then the form exactly reduces to that of plane waves. Again, the phi hat and theta hat directions are along these planes, okay, orthogonal directions, and the wave is propagating along the radial direction. So this is exactly like a plane wave. Okay, so here in this simple example, you see therefore that at large distances, firstly, 1 over r terms are the terms that contribute to radiation and non-trivial power, which is moving out and leaving the sources. They are leaving the origin and moving out. Okay, so that is the term that is going to be relevant, the 1 over r terms. And the other thing that we notice is, if we look at a specific direction, then this is almost like plane waves, right? So these things I would like you to focus. And now this is the point, that the electric and magnetic fields are ill-behaved near the origin because they go as 1 over r. So now the question is, what is the source, or what kind of source is giving rise to this kind of waves, or which can give rise to this kind of waves? That is what we are going to investigate now. Okay, so we'll now look at the sources that gives birth to this kind of radiation of spherical electromagnetic waves. Okay, so with that, we move on to our next section. So how are we going to understand that phenomenon? Okay, so the strategy is going to be very simple. What we are going to do is, we are going to take our retarded solutions and find the 1 over r component of the electric and magnetic field corresponding to the retarded solutions when we are given an arbitrary charge density or current density. And once we take that 1 over r terms, those radiation field terms, and we compute the Poynting vector and the average power, then we'll see that there is some power, or those are the terms in the electric and magnetic field that kind of becomes electromagnetic radiations far, far away. So the strategy is very simple. Take an arbitrary source, consider the retarded solution, and do a multipole expansion of that to capture the 1 over r terms. That is what we have to do, and find the corresponding electric and magnetic fields, and from there we'll be able to know what is giving rise to this kind of radiation fields far, far away. So yeah, by the way, that far region where we have this electromagnetic radiation, that is also known as the radiation zone. Okay, so these are terminologies which are interchangeably used. The region far away, this is sometimes referred to as the radiation zone. Okay, so something is happening here, as you can see in this diagram. Something is happening here, and we are interested in the electric and magnetic fields far, far away. So that is going to be the radiation zone. So we have already done multipole expansion before in magnetostatics and electrostatics. But here, there's an important difference that here now the sources are dependent on time. Not only they are dependent on time, it is not, so if I want to find what are the fields at a particular value of time t, then the time for the sources is not exactly this time, but it is the so-called retarded time. So we have to consider the sources at an earlier time. Okay, so this retarded time is basically determined by the distance of the sources to the point where we are measuring the electric and magnetic field, or to the point where we'll be seeing the electromagnetic radiation. You know, that distance goes in non-trivially into this formula, and that gives you the so-called retarded time. This combination is the retarded time. So now if we want to do a series expansion, a Taylor series expansion at a distance large, at a large distance far away from this from the source. So we choose our origin inside the sources. Okay, so this is our origin. Okay, and we are interested in distances far, far away. So then we just do a Taylor series expansion. So these terms we can expand. So this is the term inside here, and this is the 1 over r term. Okay, so that is there. Now, correspondingly, we can expand the sources out because there's a dependence on r, so we can expand the sources out in this way. Okay, similarly for the current density, also we can do a expansion, Taylor expansion for the time. So now you see that if you now do a Taylor expansion, then these terms have a dot. Here by dot I mean a time derivative. This means del t of j. Okay, this means I'm denoting a time derivative by a dot, as it is usual in physics. So these sources will also be expanded in terms of their time derivatives in this multipole expansion. And this is something which is going to be crucial. So now if we take this, let's consider the vector potential. Now if we take the vector potential and if we take the vector potential and try to find out the leading order terms in this expansion, then there will be two terms that would be of interest to us. The first term is going to be this term, j by r. So as you can see, if we expand j, then we get this is the leading order term. And if we expand out, 1 over this quantity, then the leading order term is 1 over r. The next term is basically j dot, and that would also multiply the leading order term to give you a term which is j dot by r. Okay, so these are the two terms that we are going to consider here in this discussion. Okay. So, of course, you can say that there are other terms here in this expansion which also goes as 1 over r. Okay, but those are the terms that can also be present. But at the moment, we are not considering those terms. I will tell you why the justification why we are not considering, or what justifies throwing away of those terms, that I'll tell you in a while. But for the moment, let us just focus on the first two terms. Of course, there are terms which are higher powers of r that can be neglected because there is we are considering that, let's say the charge density is limited to a region of space of radius r, and so let's say they are limited to a place of radius r, and we are considering the fields at a distance far away. And if this capital R by small r is small, okay, then that justifies throwing away of the terms which are higher powers in R in this expansion. But even for this particular power in R, there can be more terms here in this series. If we just take this time series, and so if we take this particular Taylor series and keep more terms here, there'll be more and more terms, but those terms will have higher time derivatives, clearly, because this is a Taylor series expansion of this argument. So they will have higher and higher time derivatives. Just remember this fact, that they will have higher and higher time derivatives. Even this 1 over r terms which are coming from here, they will have higher and higher time derivatives. Okay, so very good. Now let us proceed. So what we want to do is to consider these two terms term by term. Okay, we consider these two terms term by term. And so the first term, essentially we can pull the r outside this integral, this first term here. We can pull the r outside the integral, then we have the volume integral of the current. Now, you have seen in magnetostatics that the volume integral of the current was 0. And one of the things that went into the proof of showing that was the fact that the divergence of the J is 0. Okay, so if the divergence of the J is 0, this term is 0. But as you know, in a more general situation where there's time dependence, the divergence of J is basically minus of the time derivative of the charge density. Okay, this is the charge conservation equation. Now, because of the charge conservation equation, this term is not going to vanish because of that equation. It will be proportional to the time derivative of the charge density. Okay, it will be proportional to that. So, because it will be proportional to that, let us perform a very similar exercise that we did to argue in magnetostatics. But now, keeping in mind that the divergence of J does not vanish. So we use this identity, a very similar identity we have used in magnetostatics, and wherever the divergence of J appears, we use the charge conservation equation to write it as the time derivative of the current of the charge density, the time derivative of the charge density. Okay, so so now we take this and plug it. So from here we know what is J. And we can, these two terms, one is a total derivative term and the other one is a total derivative term and the other term is basically this term. Okay, so if we plug it back in here into the definition of J here, the volume integral of that, then we see that there are two terms. There's this total derivative which by divergence theorem becomes a surface term. So this is the boundary of the volume V. Okay, and if this volume integral, let's say the charge is localized, so if we do the volume integral over a distance where charge density is at 0, then the boundary will not have any contribution. So this term will basically vanish. Okay, because the charge densities are localized, and therefore this boundary integral is just 0. Okay, so this boundary term does not contribute, but there is a contribution from the divergence of J term, which now is written in terms of the time derivative of charge density. Okay, so let us see what this term looks like. Of course, this is a time derivative, so you can pull it outside the integral. But now if you look inside the integral, then this is exactly what you would call the dipole moment of the charge density. But this dipole moment, as you can see, the x is the variable which is integrated over, but this time dependence in the dipole moment will remain, and therefore the dipole moment in general for a time dependent charge density, the dipole moment is going to be time dependent. Okay, and therefore because this is in retarded time, so the dipole moment also should be in retarded time, and there should be a time derivative of it. So this is the term that we have. So we can simply say 1 over r, this thing is the time derivative p dot of p dot by r. Okay, that it reduces to that. Okay, just by using this identity, we have to use this identity, the similar thing that we have already used in magnetostatics and electrostatics. There I gave you a more detailed way to understand this, but I am just writing it more compactly here. Okay, so so now that we can do. So this, therefore, one term is done, and we see that therefore because of this, if we go back in the vector potential, this term is nothing but the time derivative of the dipole moment. Okay, now let us see what this term is. So if we try to analyze the second term, so the second term can be written down like this in the component notation, where this I index is contracted with this I index here. And now again, if we use an identity like this, okay, this again very similar to what we did for the case of magnetostatics, then we will see we have to be careful again that the divergence of J is not 0. Okay, so here now it's the divergence of the time derivative of J, but again the time derivative you can pull out and rewrite the divergence as the time derivative of charge density, but then there was already one time derivative here, so this becomes the double time derivative of charge density. Okay, so this term remains as the double time derivative of charge density. And then, of course, there are two more terms. One term is this term, which is minus of this thing, and then there's a total derivative term. Okay, so now we can use this thing here, the same drill, that we can write xijj dot as two terms and divide by half. And after we do that, we can rewrite one of these terms using this identity here. Then we get, so there's one term which is minus, so this becomes xijj, this thing, ij, and this ji, it gets interchanged with the sign. And then we have a rho double dot and a total derivative term. Again, if our current density is localized, then this total derivative term vanishes. And because of the similar algebra that we had here, we can write this as basically, as in this form. Okay, using this notation, using the epsilon, index notation, we can write this term in this form. And if we plug that back in here, then we will find that ultimately we are able to write it as x cross j dot. And of course, there's a cross with r hat because of this epsilon, and then this term essentially, this half of this thing. If we pull the epsilon out, then the half of this thing is nothing but the magnetic dipole moment, and so therefore we have a magnetic dipole moment. But then there is a dot here, so it is the time derivative of the magnetic dipole moment cross the r. The cross comes from this epsilon here outside. Okay. And you can check if I have got the signs right. So, do check it once. Okay. Now, apart from this, there is another term that we are left with. And this term is nothing but the xij rho double dot. So, of course, these time derivatives you can bring outside. Then we will have something like xx rho integral of that. That very much resembles or smells like the quadrupole moment. Of course, the quadrupole moment was 3xi xj minus x squared delta ij, that was the term there. But here this is almost like that, except the delta ij term, this is almost like that, and therefore anticipating what is to come, I'm going to call this with the notation q, and anyway I'm going to call this electric quadrupole term. And we will see, how, what happens to that additional term. We'll see soon, what happens. So basically, we are going to use that here. So this is the thing that I have mentioned. So the original quadrupole moment is basically this object, but here we are going to we have a slightly different object, which we are also going to see that this term can be written down as this term. In the relevant cases, we'll see. I'll describe to you in a while. Okay, why that is possible. But in essence, we see that these two terms in the vector potential, these two terms can therefore be written down in terms of the three terms. One involves the single time derivative of the electric dipole. So this is ED. And one involves a single time derivative of the magnetic dipole here, and the other involves a double time derivative of something which is something like the electric quadrupole. So I have written this as the electric quadrupole term, and we'll soon see how that is directly related. Okay, so please distinguish my notations. Here this is a simple Q, and this is more like a script Q, my attempt of writing down something which is a script Q. Okay, so these two things are in general slightly different. There's this additional term which is slightly different. Okay, so apart from that, we have these three terms: electric dipole, magnetic dipole, and electric quadrupole. Okay, and similarly, there are higher and higher moments that contribute even to this 1 over r term. So I'm not saying that I have written down all the terms in 1 over r expansion. That I haven't, because there are more and more terms in this expansion, and as you can anticipate from this trend, that these more and more terms will have higher and higher derivatives of time. Okay, that is the important point, that the higher and higher multipoles occur in this expression for A with higher and higher derivatives of time. Okay, so let's remember that. I will have something to comment about that very soon. Very good. Now, So essentially these are the 1 over r terms in the vector potential. Very good. Now we want to find what is the magnetic field due to these leading terms in the 1 over r expansion. Okay, so if we want to find what is the magnetic field, we have to take the curl of the vector potential. Now, if we have to take the curl of the vector potential, we are not only interested in all the magnetic field, because anyway we have thrown out terms in this expansion. So we are not interested in the entire magnetic field, but we are interested only in the 1 over r terms in the magnetic field, because of the reason that we saw in the example that we discussed initially. Okay, so we are interested only in the 1 over r terms. That's why I have written that here, that we are interested in the 1 over r terms. We take the curl and we keep only the 1 over r terms. Now, we notice one thing. Let's do it term by term. If we take the first term here, okay, we notice that there's a derivative of the curl, and then there is a 1 over r piece here, and there's a r here. So the derivative here will hit both these terms, right? And there will be non-zero result. But if the derivative here hits the term in the denominator, then that is going to give me higher powers of r. So the only way the derivative can act is by acting on this r inside the retarded time of this dipole moment. Okay, so keeping that in mind, we can almost turn it into a mnemonic. Of course, I have, you can write out the components and see it for yourself that this is correct. But you see, what happens here, what the result is this object here. Okay, so the idea is, whenever we have to take this derivative, you can replace this derivative with a minus, you can replace it with a minus r hat by c and take the cross. Okay, that's the idea. So here, this curl, of course there's a 1 over r, then there'll be a r hat minus r hat by c cross p. Now this will have a double dot. So you take a cross with minus r hat by c and you increase one of the dots here, okay, and that will give you the leading order piece or 1 over r piece when you take the curl. So this is a very useful thing to remember while taking the curl, that this is more like an algorithm. Whenever you see the curl, you put in one dot and replace this by minus r hat by c. Okay, the minus r hat by c comes because the derivative goes and hits this r here. You can see this more precisely by writing it out and taking the derivative and acting it on the various terms, and then you'll see that this term, there's a minus r hat by c that comes in, and that gives you this expression here. Okay, so that's like, but if you remember it in this way, that it doesn't act on the denominator, it acts only on retarded time, therefore it increases one derivative, and the curl essentially becomes a cross product with minus r hat by c. Okay, that's what happens. Okay, so you can remember in that way, and this is therefore the result due to the first term, and this is the term 1 over r term that contributes to the magnetic field because of the first term in the vector potential. Okay, there's a double dot here. Very good. So now you can apply the same mnemonic for the magnetic dipole as well. So the magnetic dipole was already r cross m double dot. If we go back in the expression for this thing, this was already r cross m dot. Okay, so therefore applying our technique, we will find that there's a r by c minus r by c, the signs are taken into account, minus r by c, r cross m double dot. Now it's a double dot because the derivative in the curl has come and hit this term here. Okay, it hit the r here. Okay, so therefore there's a double dot. Okay, I hope this algebra is clear. It's a very simple thing. If it is not clear, please work it out by hand. You will see that this is exactly what is the case. Okay, so I will encourage you to just practice it out once. Very good. Now what about, so this is again, so even this term, this term r dot q double dot. Okay, so this term here I have used a notation. So let me explain that notation a little bit. I have done that before. So essentially, this is like something like r hat I. This is like qij, right? So as you can see, this qij has two indices. One of them is contracted with r. Therefore, you are left over with one index. So after this dot product, basically you would be left over with a vector. And therefore, objects like this are often denoted with two arrows on top. So basically when you say that you have two arrows, then it has two indices. Q with two arrows have two indices. And if you take a r hat and dot it, one of the indices is gone, then this is like a vector. Okay, so if this is like a vector, then we can apply our this thing again, and we can convert this into a curl. Okay, so we can take the curl on this very easily by applying our algorithm. So before we do that, let me do the following here. Because this is not yet the full quadruple moment, let me add to this term, x squared term that we are missing, and subtract that term out. Okay, so add and subtract, I mean minus of this and plus of this. So this is like 0, so it is like adding 0 to this term. Okay, but once we do that, then this first term gets converted into the real quadruple moment, and we have a term like this, and we have a term like this where we can take the delta ij outside, and this is rho double dot x squared. Okay, and this delta ij, when I contracts with I here in the r hat, this will be a term r hat j. So basically this term therefore is pointing along the r hat direction. Okay, this term is pointing along the r hat direction. Now if we take a curl of this term which is pointing along the r hat direction, then you know I have to take this object and basically take the cross product with r hat by c, minus r hat by c. And because of this cross product, you see, this r hat cross r hat, that is going to vanish. Okay, r hat cross r hat is 0. Therefore, this term will have no contribution in the magnetic field. Okay, so as far as the magnetic field is concerned, whether this is this q or the actual quadruple moment, you know, it's the same thing. Because in the curl, you know, this additional term being curl free in this sense will not contribute to the 1 over r power of the magnetic field. Okay, because this is not going to contribute to the 1 over r power of the magnetic field, therefore we can forget about this term and just convert the simple q into the quadruple moment q. Okay, that's how it works. So if then again now we have to take the curl of this. So basically, you know, this is exactly what I told you. The curl of this thing vanishes, and then basically we will have this curl to evaluate. Then by our simple thing, that algorithm, you know, convert this into this thing, and this is a cross. So you can write it down in terms of indices if you like. So this is r hat cross this term. But now notice there was a double dot to start off with. So in the magnetic field, there's 3 dots, the triple dot term. Okay. So basically putting down all the radiation magnetic fields together for this arbitrary source, that means radiation fields meaning 1 over r, you know, fields that go as 1 over r. So that if you now track, then there are 3 terms. One corresponding to electric dipole, double derivative of the electric dipole, and the other corresponding to the double derivative of the magnetic dipole. And the third term corresponds to the triple derivative of the electric quadrupole. And so there are more 1 over r pieces. I'm not saying there aren't any 1 over r pieces, but there are more and more 1 over r pieces. But those are, you know, those terms are also suppressed in a particular sense. So let me explain that point. You know, why those terms are also suppressed. Okay, so that is a very important point. And there was a question in class about this, so let me explain that point once more. So you see what is going on here. There are essentially in this problem there are 3 length scales. Okay, if we assume that charges are oscillating with some kind of a frequency, then there are 3 length scales in the problem. The first is basically, let's say there's some charge density. Okay, so let me actually use the pen for it. You know, just yeah. So basically, let's say there's some charge density. Okay, which has a length scale, which is let's say this length scale is some given length scale. Let's call that L. Okay, and we are interested in finding the electric fields at a distance which is, let's say, r. Okay, and then also we see that these things are oscillating. Because these things are oscillating, this oscillation has a frequency, and you can take that and convert into a k, and that will have a corresponding lambda. Okay, that will have a corresponding wavelength. So that is again another length scale in the problem. Okay, so basically there are these three length scales in the problem. It's a dimension full quantity. But out of these three length scales, you can construct two length scales, a two dimensionless quantity. One is basically this L by R. Okay, this is one dimensionless ratio. And the other object is essentially something like omega C times L. Okay, so you see, if so there are certain terms that are subdominant because this is small. Okay, and if you consider the terms that are higher and higher powers or higher and higher time derivatives of the moments, then this is suppressed by a factor which is like this, omega L by C, where L is the typical length scale of the charge distribution. Okay, so this is another length scale in the problem which we have, because we are talking about waves here, or like oscillations here. So therefore this is another typical length scale that we have. And basically, if we consider a case where these frequencies are small or the wavelength is large. Okay, so if the wavelength is large compared to the dimension of this charge distribution, if the corresponding wavelength is large compared to the dimension of the charge distribution, then these higher terms that we have, they can be neglected. Please notice that these terms are essentially 1 over r. So all these terms that have higher derivatives of the moments, they have the same power of L by r. Okay, they have the same power of L by r, but they have different powers of omega L by c. Okay, so if omega L by c is also small, okay, this is again dimensionless. So this is a, it's legitimate to call it small. Okay, I cannot change units and make it large or small. Okay, so in that case, I can always ignore these higher and higher terms that have higher derivatives with respect to time. Now, I should I should make one more comment, that you might ask that where is the L here? Where is the L here? The L is actually in some sense hidden, because if you consider these terms, for instance, this one, then you see this one is going to be x times rho, and this one is going to be x times rho. So basically this has a higher power of the dimension of this charge configuration compared to just x times rho, which is the dipole moment. Okay, so compared to this has one more higher power of the dimensions involved compared to this term. So obviously this term is suppressed compared to this one. Okay, so in this way, this higher and higher multiple moments, they also contribute to radiation fields in the sense that they have this 1 over r dependence. So basically they are same as far as L by R is concerned, this parameter is concerned. They are the same order, but they are suppressed with this other small parameter in the problem. So we are assuming that the wavelength of emitted electromagnetic wave, that is going to be large compared to the size of the typical size of the sources that are giving rise to these waves. Okay, so under that approximation, you can basically ignore all this term, and if that approximation is not valid, then you have to deal with those terms and keep them in your analysis. Okay, so in this sense, for large wavelengths, this term is also subdominant compared to this one, and so as I will try to show you that this term is also subdominant compared to this one. So this is at large wavelength, this electric dipole term is the dominant contributor to radiation. Okay. So this was just if you like, a sidetrack discussion. But then we have these three terms in the magnetic field. Now, because we have these three terms in the magnetic field, we can go ahead now and compute the electric field. Now, you might imagine that to compute the electric field, we can start with the potential and compute it. You can do that, of course, but there's an easier way. Because now we have an algorithm to take curls and extract the 1 over r piece. Therefore, there's an easier way to do that. And the easier way is to use Ampere's law. Okay, so we know that the source is doing something here, but we are interested in the fields far, far away, which is the radiation zone. And in the radiation zone, there is no sources. So in the Ampere's law, we will have no sources in the radiation zone. So if we don't have any sources in the radiation zone, we can use Ampere's law and find the corresponding term in the electric field corresponding to the B field. Okay, and basically we have to take one more curl and then integrate with time here. Okay, that's what we need to do. Okay, now we are experts in taking curl now, because curl essentially what? It becomes the cross product of r hat by c minus cross product of this. This curl becomes. Okay, that we are experts. So therefore it's easy to do that. Okay, so because of this algebraic simplification, I'm trying to follow this process. If you want, you can go back and use this description as well. You should get the same result because all the equations are consistent, right? All the equations are consistent, so we should get the same result. So now we start with, therefore, there are three terms here: the electric dipole, the magnetic dipole, and the electric quadrupole. And we take a curl, and we have to multiply by c square also. This is something important. And if we multiply by c square, and then finally we have to integrate with time. So as I said, if you take a curl, then everywhere where you take a curl, you have this 1 over r, minus r hat by c everywhere. This is the action of the curl. Not only that, you have an additional time derivative. So here there's 3, 3, 4. So here, as you can see, there's 2, 2, 3, and one time derivative increases here. After you take the curl, there's one more time derivative, and there is a cross product with one more r hat piece. Okay, so that is the idea. Okay, so that's very simple to do. But now, as far as taking the time integral is concerned, you can just take this and integrate with time, and you set initial conditions so that the constants are all 0. So if you integrate with time, you will reduce one of these dots if you integrate with time, because these are the only quantities that have the time dependence here. These are the only quantities that have time dependence here, and therefore you will reduce one of the dots here, right? And mind you, this is not just ordinary time, this is retarded time, but then in the retarded time there's a t here, so the time derivative acts directly. Okay, so very good. Okay, so basically we see, therefore, in effect, what this curl, use of this this algorithm of taking curls and doing the time integral again, that tells us that clearly the electric field is minus c times r hat cross b, because the curl gives me r hat by c. Okay, increases one dot here, and that you multiply by c square, so that one factor of c cancels, and therefore it's c times this object. The minus sign remains, and the extra dot is removed because of the time integral. Okay, so this relation is clearly valid just by the way in which we have done the calculation. But this is also the condition that is satisfied by propagating electromagnetic waves, as you know very well. So in fact, as we can see that from all these terms, both the electric field and the magnetic field, because of the r cross here, we see that both the electric field and magnetic field are perpendicular to the r hat direction. Okay, and they also satisfy this condition that the electric field is perpendicular to the magnetic field. Okay, so basically r hat, the electric field and the magnetic field, they form three mutually orthogonal vectors, just like in electromagnetic waves. Okay, very good. So now, of course, there's this one term where there are too many r's here. R cross, r cross, r hat cross, r hat cross, r hat. Okay, so basically we can we can simplify that. Okay, you can use your if you remember your vector identities, but I prefer to do it using the index notation. So if you just do it and simplify, you will see that this 3 r crosses just reduce to, you know, 1 r cross. Okay, given any vector. Okay, so for all the you know, this term here, this v vector is this m double dot. Okay, so for that it reduces to this thing. Okay, so therefore we change this term and write it in this way. So again, the electric field also has the same form as the magnetic field, but the electric field has the same form as the magnetic field, but we see that there are these time derivatives. Okay, and there are you know, the 1 over r, it's a 1 over r expansion, leading order pieces, but even there we are neglecting these higher order multipoles, and they're, you know, because they have higher number of time derivatives. And if we assume again that parameter omega L by C, that is small, then we can ignore these higher order pieces. Okay. Sorry, I have a mistake here. Right. So this is omega L by, sorry. Right. Okay, so I'm assuming that in my mind, I'm assuming that these have, you know, this, I'm assuming that these time derivatives, you know, these time dependences of the moments, they are like harmonic functions. Okay, that I'm kind of assuming in this. I mean, even if they are not harmonic functions, you can think of again, you know, there can be more than one frequency, but if there is like, if this is true for all the frequencies that are being emitted, then this is going to be true again. Okay, so right. So right now, what we are going to do, so we have the electric field and the magnetic field obtained. We have obtained that. Now we are going to look at these 3 individual terms separately as so let's say if we just consider one system with electric dipole moment non-zero, and let's say these things are 0, okay, then we can focus on only electric dipole radiation. Okay, the radiation due to electric dipole. Okay, so it's very important that we have a time derivative here. Okay, it's very important that we have time derivative here, so we look at this term by term now. And so let's do that. Let's look at this electric and magnetic fields term by term. So again, we consider one system where the electric dipole is oscillating. Okay, with some, you know, it has a time dependence. Okay, in general, it can be a non-trivial time dependence. And so if we consider that, then we will see that the electric and magnetic fields at far you know, distance behaves in this particular way. Okay, so now the drill is basically the same drill, the same set of exercise that we did initially. So of course these relationships are satisfied. They are in general satisfied for the entire radiation field, you know, that we have written down. But again, in particular for this case also they are satisfied. Okay, and not only they are satisfied, if we now take the Poynting vector and compute it, so we can use one of these relationships and convert it into the magnetic field square. So the Poynting vector, we can just convert it into the magnetic field square pointing along the r hat direction. Okay, because the magnetic field is perpendicular to r, so this term vanishes. So so basically this is the magnetic field. So I just encourage you to go through this algebra once. Okay, you can do it once, but you know, essentially you have to calculate these 2 cross products, which you can do using, if you remember your identities, it is basically given by this expression here. And here, because the magnetic field itself is perpendicular to r hat, therefore this term will vanish and will be left over with a term which is r hat times the magnitude of magnetic field square. Okay, equivalently, this I can also write as r hat direction magnitude of electric field square, and where this term is going to get the coefficient will adjust itself. The dimension will adjust itself. So basically, I think the C will come in the denominator, and we can write this as also r hat times electric field, a modulus of the electric field square. Okay. So now, so if we have this, and we know that the magnetic field behaves in this way, we can try to take the square of the magnetic field. Then this is basically dotting these two vectors. So if we dot these two vectors, that means, we have to find the mod of this p double dot square. This thing is this vector p double dot square. We have to find. Right. So yeah. So right. So yeah, I mean, that's the exercise. For the Poynting vector, you find the mod of this vector square, and it is pointed along the r hat direction for the radiation fields. The way the radiation fields are arranged, that this Poynting vector always points along the r hat direction. Okay, for the dipole, for the dipole. So basically, this is the same drill, and if we therefore now integrate this, let's say for an infinitesimal element on a sphere of large radius. Okay, so here some dipole is oscillating. We try to find it on some infinitesimal element. That infinitesimal area element is given by this object here. And again, because of the 1 over r, r square dependence, 1 over r dependence of the electric field and the magnetic field give rise to a 1 over r square dependence in the Poynting vector. So that r square cancels out this r square in the area element. And then this part that we are left over, this is the element, solid angle element. Okay. So this infinitesimal power that goes into one of these solid angles, so that is sometimes written in this way, dp d omega. So you take this and basically, you consider it per unit solid angle. Okay. And that is basically given by this expression here, where you have to find the time derivative of the dipole moment, cross it with r, and take the mod square. Okay, that's all you have to find to take this. So this actually is a quantity which is of interest also, because it tells us the angular dependence of the emitted power. So it can happen, if I consider this sphere, it can happen that certain power is moving through this direction more, and compared to this direction where, let's say, there is less power. Okay, it is possible, and that angular dependence is captured in this power emitted per unit solid angle. Okay, dp d omega captures that angular dependence non-trivially, and therefore this is also a quantity which is of interest, because we want to know in which direction power emitted is more compared to the other direction. Okay, and as you can see, we need a time derivative of the dipole moment, which would give rise to this radiation or this power far away. This cancellation is going to happen, and because of the reason that we discussed in the initial example, this part of the electric and magnetic field is just going to leave the dipole moment, and they're going to move away from it. Okay, of course, you will have other powers of the electric and magnetic field. Those powers are going to die away. But this object, dp d omega, as you can see, is independent of r. Okay, that means that this amount of power per unit solid angle, that kind of leaves the fields and, moves away to far off infinity. Okay, that is always constant, no matter how far you are. So these radiation fields are the fields that are leaving away the sources and moving out to infinity from the sources. Okay, so the idea is this: there are source and there are some electric fields that are bound. Okay, and then the radiation fields kind of move away, and they move away because the amount of power, integrated power, is always the same no matter how large a surface that you consider. Okay, so the radiation fields kind of leave the electric fields and they fly away from the oscillating dipole moment. Okay, so that is the idea. Very good. So now again we can take this and find the time average. So that is the usual quantities of interest. So given any oscillating dipole configuration, we can find this object and then take the time average of it. Okay, and then you can not only take the time average of it. So it is recommended that you do that, as we that is a very physical quantity. Okay, of course this is dependent on time, but if you take the time average, then this makes a lot of sense that what is the average power that is moving out. Okay, This is something, and then we can find the total power by integrating the power per unit solid angle over the full solid angle. Okay, so this is the solid angle. This is the solid angle that I'm referring to. So this is ds. It is directed in this way. This r square cancels with the 1 over r square coming from the pointing vector, and there's an oscillating dipole here, and there's some power that is being emitted in all directions from the oscillating dipole. Okay, and this sphere is large. No matter how large, this will not have any this total power will not have any 1 over r dependence, because the pointing vector for the radiation fields goes as 1 over r square. I hope I have emphasized that point enough, and this is something which you can find. So very good. So now the point is that you have to consider various situations and evaluate these formulas. Okay, basically this is the formula that we need to evaluate. Now you see we have a changing dipole moment here. Okay, so the dipole moment can change with time in essentially two different ways. One way in which it can change with time is that, let's say its direction is fixed. Okay, it has a fixed direction. Okay, and its magnitude is changing. Its magnitude is fluctuating with a fixed direction. Okay, so that is an example that I have. I've worked out a couple of examples here. So that is an example like this. Let's say you have two spheres, plus q and minus q, connected by a wire and drive a current through it, so that the charges are fluctuating among the two spheres. Okay, so that is going to change the dipole moment because the charge is fluctuating. So the dipole moment will change with respect to time, but the direction of the dipole, z direction, that is going to remain fixed. Okay, so this is one of the cases in which dipole radiation can happen. So if we take that now, again you can consider this distance to become very small and consider an ideal dipole, and q naught goes to infinity with p naught fixed. The same way in which we considered an ideal dipole that you can do. And if we did that, then we can go ahead and compute this object. We plug it in the p double dot here. Okay, because of the two time derivatives, we essentially get a factor of omega square here inside, and basically the r hat and the z direction gives me a sine theta. Okay, this is, we are choosing the direction of the dipole to be the z direction so that we can get a sine theta here. Okay, and once we do that, then we have, of course, the cos square, the harmonic part becomes a square, and so this is the result. This is the result for dp d omega. Okay, this is the power per unit solid angle. Now the average, you will just average over cos square, and that is going to give you a factor of half here. Okay, that is going to give you a factor of half. And the omega, because it was inside the square, this omega square, therefore this goes as omega to the 4. Okay, this omega to the 4 is also very, very important. Okay, this is not only, so there are two very important aspects of this formula. One is this omega square, omega to the 4 here, and the other is this sine square theta. So this is the angular dependence in which power is emitted. So we see that when a dipole is oscillating like this, power is emitted along like a torus. So basically, if I have an oscillating dipole, power is least along the theta equal to 0 direction, and it is maximum in the perpendicular direction, right? Because of the sine square theta, right? So this is something, this sine square theta is therefore also very, very important. So I have emphasized them here. These are the two things that are remarkable about this formula. The fact that it goes as frequency to the 4, and the fact that it goes as sine square theta. Okay, so very good. So this is the, if you do a polar plot, then this will be something like this, right? This will be, so if this is the z-axis and this is theta, okay, the polar plot will look something like this. Sine square theta would look something like this. So maximum power is emitted in the perpendicular direction, and in this parallel direction, no power is emitted because of the theta thing here. Very good. Now you can compute the total power, integrate it. So basically you have a sine theta from here. So you have a sine cube theta integral. The phi integral gives you a 2 pi factor. So the phi integral gives you a 2 pi factor, and this thing, and then this is a very famous formula. Okay, the total power goes as omega to the 4, goes as the dipole moment square, and it's basically, this factor of 12 is also, kind of remarkable. Okay, this factor of 12 is something very useful. This formula is sometimes called the Larmor formula. This formula itself is called the Larmor formula, but the Larmor formula actually originally referred to as to the point charge. Okay, so let me briefly describe that now. I will describe the point charge in more detail in the next video. So so basically, if we have, let's say, a point charge which is oscillating in a fixed d length. Okay, you take a point charge which is oscillating like this. Okay, then this is the displacement vector for the point charge, and the dipole moment is going to be q times this displacement vector with respect to any origin. You choose origin, let's say, so basically this vector is with respect to some origin, and the dipole moment is defined with respect to the same origin, and it's q times d, as you know. Okay, dipole moment is x rho. So rho is a delta function. So this is like q times delta function. So this is q times d. Okay, and this d is changing. D is changing now. So if the d is changing, then if we take the double dot, then this simply becomes the acceleration, right? This simply becomes the acceleration. And now if we so now you see, because it's the point charge. Okay, so it's not really, this. So it can be moving in any way, not only in a harmonic way. It can be moving in any way. And if it moves in any way, then this p square here, we can, from this p square here, this thing, we can say that this is some, it's, let's say, it's oscillating along the z direction. Then it becomes mod of this p whole square, and that will give us q square a square in this formula. Okay, this is, again, here we haven't done the time averaging, so it's not 1 over 12, but it's 1 over 6. Okay, so this is the formula for which is called the Larmor formula for the moving charge, and this is the sense in which it is there. But sometimes this formula for the dipole is also referred to as the Larmor formula. Okay, but we are going to do the point charge. I'm not doing it very seriously here, because we are going to do this again in the in case of when we deal with the point charge more seriously. So if the thing is really harmonic motion like this, then a will also be a harmonic function, and then a square will be a harmonic function. Okay, it will be something like, it's a double derivative, so it's again going to be a cos. It's going to be a harmonic function again. So now if you take the time average over this, then you will get a factor of half, and that will make it 1 over 12. Okay, so that is something that happens if we do the time averaging. But without that, sometimes this formula is quoted without the time averaging. Sometimes it's quoted with time averaging. So you will see this thing becoming either 12 or 6, and various people will refer to that as the Larmor formula. So basically all these things, the dipole, the point charge, everything is sometimes referred to as the Larmor formula. So, it can be a little confusing what is the context, but from the context it should be clear, what you're talking about. Okay, I will give you some more exercise on this thing, how to work it out. In your assignment sheet, there will be more exercises so that you have some practice in finding out electric dipole radiation fields and electric dipole, like the power or, dp d omega in case of electric dipole oscillations. Okay. So before I move on to the magnetic dipole, let me make one small remark here. So you might think that this time derivative in the dipole moment is arising out of this time derivative in the dipole moment is arising out of some time derivative on the charge on the charge density, right? This time derivative on the dipole moment is coming because we say that this is xi rho double dot. Okay, integral. Okay, so this is what the time derivative means. So you might think that whenever there is a time dependent charge density, whenever there is a time dependent charge density, there is dipole radiation. You might wonder, or there is radiation. Okay, but in general, that is not true. Let's say there is a very interesting counter example that if you have a charge, let's say a charged sphere, a spherical symmetric charged ball, where there's some charge q which is distributed throughout the charged sphere, and if you take that charged sphere and fluctuate its radius, let's say small fluctuation of its radius you perform, then the charge density, because the charge, same amount of charge is distributed uniformly. So, and you're changing the radius, so you're changing the volume, and therefore the charge density is fluctuating there. Okay. But although the charge density is a function of time in that example, if you compute the dipole moment, because it's spherically symmetric, you will compute the dipole moment would vanish, or the time derivative of the dipole moment would vanish. So although there is a time-dependent charge density, if the dipole moment and its time derivatives vanish, there is no radiation. So these are the basic things. You need the time derivative of the dipole moment, magnetic dipole moment, or quadrupole moments, etc. You need the time derivatives to be non-zero. Not only it's the time derivatives to be non-zero, you need at least the second time derivative to be non-zero. Okay, so if at all there is a situation, very unlikely, but if at all there is a situation where the first time derivative is non-zero, but the second time derivative vanishes, some very concocted situation. So in that case, also there will be no radiation from any source, from that particular source. Okay, there will be no radiation at all. Okay, so therefore, this is something which is good to keep in mind, that time derivative of current density and charge density, that always doesn't immediately imply radiation will happen. It's basically the moments, the dipole and the quadrupole and all these moments that have to have a non-trivial time derivative, and only then there will be radiation. Okay, this point is something which one should appreciate. Okay, now let us move on to the magnetic dipole radiation. So now you are familiar with the exercise, or the, what is the drill, that what you have to do. So basically these are the two terms. Again, I'll just go through this very quickly. You can go through the algebra yourself a little bit carefully. So you have these two terms for the magnetic dipole moment, the electric field and the magnetic field. So again, they satisfy this identity here because of the simple way they were actually calculated, remembering the way in which they were calculated. So they satisfy this. So now, again, the E and the B are also perpendicular to r hat. So you can just take a r hat and cross it. You will basically get this formula here. Okay, so these are, always valid for these radiation fields. It simply follows from the way they were calculated in the first place. So now you can compute the Poynting vector, and because here the electric field is somewhat simpler than the magnetic field. Okay, so we can basically use the electric field, eliminate the magnetic field, and write it as the electric field mod square times r hat. It's the same exercise as in the dipole. Okay, same steps. So basically, now you just take this and find the mod of this thing square. So it's r hat times the magnetic moment double dot. Okay, of course it's retarded. This simplifies. This implies that I have to consider the magnetic moment, double dot, at the time t minus r by c. Okay, we have to consider the retarded moment. Okay, so if we do that, then basically we again try to find this the differential power, or the power emitted per unit solid angle. That is again basically the same expression here. Okay, apart from there's some factor readjustment which essentially takes care of the unit change, because now we have the magnetic moment rather than the electric dipole moment. Okay, so that is something, and from here you can again compute the average power per unit solid angle and the total power just by integrating. Okay, so let us see this in a couple of interesting examples. So the first example that you can consider for magnetic dipole radiation is this particular example, where you have where you have a current loop, and basically some alternating current is flowing through this loop. Okay, I will just outline these examples. Okay, please go through this example in slightly more detail and work it out yourself. These were supposed to be exercises, but given that we have little time constraint, so I'm basically going through these examples with you. So now we consider this loop let's say a circular loop, and then basically if we compute the radiation fields, they'll be interpreted as like radial waves or spherical waves that are that would be emanated if there is a time-dependent current flowing through this wire. Okay, and basically who will do the work in, like, will put in the energy? The system that actually drives the current here, that will give the energy. So part of the energy is going to go out as this radiation. Okay, well, that part of energy is basically very tiny compared to the, let's say, the energy that goes into, like production of heat along this conductor, etc. But nevertheless, there will be a fraction of the energy that goes out as radiation, and that is the energy, or that is the total power that we are trying to calculate here. Okay, power meaning energy per unit time that is being emitted as radiation. So again, so for this, we know that the magnetic moment is area times this current, and the current has this form. So this is m naught times cos omega t, and again, because the loop direction is not changing, so it is pointing in a given direction. So this is very similar to the case that we had, that we have a magnetic dipole along a particular direction, but its magnitude is changing. Okay, because of the time varying current, the magnitude is changing. And again, so dp d omega you can calculate in the similar way, r cross this thing. So again, you can take this to be the z hat direction, then you'll get the sine square theta out, and this will be a mod of m double dot square at retarded time. Yeah, so yeah, this is a little bit of a mistake actually. So this is, this I should, technically write, this thing, because this is at retarded time, I should write this as cos of omega, let's say, omega t minus r by c. Okay, that is technically more correct. Okay, and that sine square theta. Okay, so that is there, and here also we should emphasize. So in the time averaging, it will not, this retarded nature is kind of washed out in the time averaging. Okay, so now if we take this and perform a time averaging, so we'll just get a factor of half here. Okay, we'll just get a factor of half here, and we will, this will be the final, the power per unit solid angle time averaged. Okay, so now again we can integrate this. Then this is again the theta integral will give you a 4 by 3, and the phi integral is going to give you a 2 pi, and then it's essentially the same, pretty much the same formula as we have seen in electric dipole. Okay, so but here I will just make one small comment. This was again because something was asked in class. You see, this m, this actually goes as I naught square, right? Because this goes as I naught square, therefore this total power goes as I naught square. Okay, so you can define an object which is this. You can take this power, whatever you have computed, you can say that this is equal to half I naught square times R radiation. So this has I naught square in it. So if you say that this is equal to this half I naught square R radiation, then this is going to, the I naught from here and here is going to cancel. Okay, and then you are going to left over with an expression for this R radiation, which you can consider as the radiation resistance. Okay, so it is like as if some amount of work needs to be done by the agency that is driving the current, and that amount of work is like being radiated so that amount of energy is like radiated in terms of radiation. So that loss of energy can be thought of as like overcoming some amount of resistance, effective resistance. And this part of the, so of course there's some, when there's a conductor, there's a original resistance, and that is there. But apart from that, there is also this radiation resistance that can come in, because this arises because there's some energy that is being spent out as radiation from this oscillating current. Okay, Very good. So this is one example. And the second example that I have here, okay, so before I go into the second example, from this expression, you can now try to compute the ratio of the magnetic dipole moment and the electric dipole moment. So this is nothing but m naught square by p naught square c square. Okay. Now, if we consider one electric dipole and magnetic dipole with similar, dimensions or similar proportions, then we can roughly say that this m naught is like, pi b square I naught. This is the area pi b square. And P naught is like Q times D. Okay, this is the distance, let's say, between the dipoles. Okay, and this basically B and D are comparable, let's say. Okay, B and D are comparable in some sense. Okay, so just for comparison, if you just set them to this. And then I is basically dq dt, and dq dt, because essentially everything is harmonic, is something like Q times omega naught. This I naught would go as something like Q times omega naught. And if we take this and plug it back in here, we see that this is, the factors cancel and simplify to, this b square omega square by c square. Okay. And again, using the equivalence between b and d, you can say this is d square omega square by c square. Okay. So you remember that we had initially considered that this omega dimension by c, this object is small. Okay. This object is small. I made a remark initially. Then you could like ignore the higher time derivatives. But we see secretly, even for the dipole moment, magnetic dipole moment to electric dipole moment, there's this factor here. Okay, secretly. And you can think of this more like the velocity. So if D is the displacement vector, then this is more like the velocity, v square by c square. So, this is typically very much less than 1. This is very much less than 1. So because this is very much less than 1, this electric dipole radiation is much more dominant than magnetic dipole radiation for sources which are of similar dimensions. Okay. Of course, there can be a very strong current here and very weak charge here, and that will be a that can in that sense, in a particular situation, magnetic dipole radiation can dominate. But in a situation where you have comparable dimensions of the dipole moments, then because of the smallness of this quantity, if it is small, okay, if the omega is such that it is small, then you can say that the magnetic dipole radiation is suppressed compared to the electric dipole radiation. And that is seen mostly in usual circumstances. This is what is seen. Okay. Very good. Now, I will not get into a lot of detail about this second example that I had. I want you to really work it out and go through this once. Okay. And this is a very interesting example, very, very interesting example. You see, this is the second type or second way in which the dipole can oscillate. Okay. So let's say there's some fixed dipole moment here along some direction, and this object is being rotated along another direction. So there's an angle between the rotation direction and the dipole moment, but the magnitude of the dipole moment is fixed. Okay, so if you have that situation, then you can write down the magnetic moment in this way, that it's oscillating. Okay, this is very similar to the situation what happens in like neutron stars, which are pulsars. Okay, and essentially they have very strong magnetic moments and therefore very strong magnetic fields. And these magnetic moments are essentially, they are also rotating in some way, and that is rotating along a given axis. So the direction of the magnetic moment, that is changing with time, and therefore even in that case there will be radiation, because we as far as this thing is non-zero, m double dot direction as a vector is non-zero, we can have radiation. Okay, so in this case there will be radiation as well. So you can again write this out and find m double dot, and again you can write out r hat and find the cross product of this, and you can do it much more simply. I have just done this. This thing is basically, you can think of this as m double dot the whole thing squared minus r hat dot m double dot the whole thing square, I think. Okay, this is nothing but r cross this thing the whole square. So if you are interested in this whole square, then it's the formula that I just wrote down. Okay, so we would be interested in mod of this square. Okay, we'd be interested in mod of this square. So, but you can just work it out, like bluntly if you wish. You can take the cross product, find the cross product, and then find the square of this thing, ijk, and then evaluate this object. And once you evaluate this object, then you can take the time averaging. You can take the time averaging. This is with respect to retarded time. So you can take the time averaging, and you'd get some angular dependence, which is like this. Again, you see this angular dependence is slightly different from the angular dependence we had before. Okay, and here you have this sine square alpha. This sine square alpha essentially is this angle here, this sine square alpha. It just enters in because it enters the dipole moment. Okay, this sine square alpha. Okay, so therefore, as you can see, it is rotating along the xy direction. This thing is rotating along the xy direction, and z direction is the direction which is fixed. Okay, so it does, the z direction therefore doesn't involve the second, enter the second derivative. Very good. So now we can find an expression for power per unit solid angle and the time average power per unit solid angle, and then integrate this thing to obtain an expression for total power radiated in terms of this angle and this rotation, this angular velocity of rotation for this pulsar. Let's keep the pulsar in mind. Okay. Now you can do something very interesting with this. So if the pulsar, you see, we find that the pulsar is like slowing down at some rate over the time. Okay. And if you assume that it is actually emitting radiation and it is slowing down over time, and basically, the loss in this mechanical energy, because it is slowing down, its rotation is slowing down, that loss, if it is, that loss in energy is entirely given out in radiation. Okay, if you assume that, then you can actually estimate the amount of energy that is given out in radiation. Okay, so you can do the following thing. If you for instance have a magnetic moment, then you can write down this total power in terms of the magnetic field at the surface. So the magnetic moment is oscillating, and this oscillation is producing radiation, but it will also produce magnetic fields because it has a magnetic moment. And just for estimate, if we say that this is a static dipole, then the dipole moment produces a magnetic field which is of this form. So just for estimate, like order of magnitude estimates, we can say that the magnetic field, the maximum magnetic field is obtained when essentially this thing is basically m dot r, this term is like maximum, right? So if m dot r is maximum, then it's mr, basically it's m is directed around r. Okay, then in that case you will have this as 3m minus m, that's 2m, and so the maximum magnetic field would be given by this expression. And now you can eliminate m naught from this expression of the total power here and write it in terms of the magnetic field as I have done here, the total power. So the total power is given by the magnetic field, and this magnetic field I have considered to be the magnetic field at the surface. Okay, this r is the surface of the neutron star. Okay, it has a radius r. This is the surface of the neutron star. So the maximum magnetic field at the surface of the neutron star, in terms of that I can write down the total power. Also, as I said, the neutron star is slowing down, so I can compute the energy lost because it is slowing down. Okay, that I can do, using mechanical considerations. So basically the rotational energy is half the moment of inertia times omega squared. And so if we consider this is a sphere, this is going to be the moment of inertia of the sphere. And from here you can compute the rate of change, assuming that there is a change in the angular frequency. It's like slowing down. So there's a minus sign, means it is slowing down. The energy is decreasing. And if this energy is entirely emitted in terms of radiation, then this rate must be equal to this total power. Okay, so if we know these parameters here, then we know what is the total power emitted, and we know what is the magnetic field. Okay, so I've just put in the numbers here and did this, order of magnitude estimate. We find that about 10 to the power 32 joules per second of energy is being emitted in electromagnetic radiation. So 10 to the power 32 joules every second is is basically that is the amount of energy that is being emitted. Okay, and so this can happen only if the dipole moment is very, very strong, and consequently this will give rise to a magnetic field on the surface which is of the order of 10 to the power 8 Tesla. Okay, that's like a huge number. If I have, see, I've just done order of magnitude estimate, so just verify if I have put in the numbers correctly. Okay, by the way, these numbers that I have taken, these are for, something called the Crab pulsar. This is in the Crab nebula. Okay, so but these are typical values of a pulsar which is slowing down. Okay, so, and if you take these typical values and if you put this in, and you will get that this is basically this thing on 10 to the power 8 Tesla. This nice example was essentially, I think, has been discussed in the lecture notes by David Tong, and essentially I have picked up this, this nice example from his lectures, and you will see that right. So you will see that this thing gives you an order of magnitude estimate of the magnetic field. And just to give you an idea, the strongest the very, very strong magnetic fields that we have in our labs, for instance, for instance, here at KGP, the strongest magnetic field you can produce is like 5 Tesla. Okay, so you can imagine how strong these magnetic fields are. Okay, so this is a very, very, these objects are very, very, so this is like an application of the idea of radiation. From the power emitted, so basically some power is being emitted, the mechanical rotation is slowing down, and if you just measure the rotation rate, how it is slowing down, okay, that from there you can actually basically try to obtain that what is the magnitude of the magnetic field at the surface of these pulsars, and that happens to be very, very high. Okay, so there's some very exotic phenomenon that happens therefore on the surface. There can be very interesting, magnetohydrodynamic phenomena that happens at the surface of these neutron stars. Anyway, so now let's move on to the next term, that is the quadrupole term. And here also, again, the drill is same. The electric and magnetic fields are known. They satisfy this relation. Okay, they satisfy this relation. So you can find the Poynting vector and eliminate one of the electric field or magnetic field using this relation. And then you can get it in terms of the magnetic field squared, and it's also directed along the r hat direction by construction. Okay, it's the same piece of algebra as before. And now basically you have to find the magnetic field square. That would involve finding the square of these two terms. So this is like a vector, and you have to find the mod of this vector squared along the r hat direction. And that is the Poynting vector. So, if you consider just this expression, that is the, forget about this 1 over r square factor. That is the power emitted per unit solid angle, and that power emitted per unit solid angle you can take and integrate it over d omega to get the total power. That is the thing. And so here in this case, again, depending on the quadrupole moment, which components of the quadrupole moment is non-zero, you will get various angular dependencies. Okay, in this dp d omega, you will get various angular dependencies based on what the quadrupole moment or what the components of the quadrupole moment are non-zero. Okay, that is something which is very, very interesting. Again, I will not get into a proper discussion of that, but I'll give you an example. Okay, and the one thing that I want to you to note that because of the 3 derivatives, there'll be a omega to the power 6 term coming out. Okay, so the 3 derivatives will bring down omega cube, and this because it is being squared, this dependence will be like omega to the 6. Okay, for quadrupole radiation, this goes as frequency to the 6. Very good. So right. So here I have an example that I have worked out for you. Again, I would like you to go through the algebra. I'm not going to go through the algebra very closely here in the video. So you go through the lecture notes once carefully and go through the algebra once. Okay. It's already a pretty long video, and I want to discuss one more thing before I finish. So here for the quadrupole oscillation, so you take quadrupole, which is plus q minus q plus q minus q here. So this is a quadrupole. The total charge is 0. The dipole moments are 0, and also if you take this and start rotating it, along this, let's say, the axis which is passing through the center of the square loop, that axis I'm taking to be the z-axis. Okay, so if you take that and rotate it, so the magnetic dipole moment would also vanish, the electric dipole moment would also vanish. So this quantity will radiate only in terms of this object, or this rotating object will radiate only in terms of quadrupole radiation. Okay, so again, now you can label the charges 1, 2, 3, 4 and find their locations. Okay, you find their locations, write down their locations as they rotate as a function of time, and then basically try to compute Qij from the locations of the charges. So these are charge density, it becomes non-zero only where the location of the charges exist. So it will be a sum over the 4 charges, and that you can just go ahead and evaluate all the non-zero components of the quadrupole moment. I will leave this to you to have a look. So these are the terms. The Q11, Q22 and Q12 are non-zero, and it is found that Q13, Q23 and Q33 are 0 simply because the Z component of these things are 0. So it is like a plane, square, and the Z axis is perpendicular. So the Z component of all these, it's being rotated in the XY plane. So the Z component is always 0. Therefore, the dipole moment along the, this, whenever this is the Z, the 3 direction, that direction is the dipole the quadrupole moment vanishes. Okay, and then the Q11 has this expression. You can just try to verify. The Q22 has this expression. The Q12 has this expression. So as a matrix, you can write down. So this has Ij component. So if you say that I is column, J is I is row and J is column, then you can write it as a matrix. Okay, and this is the form of the matrix where the Z components vanish and the XY components are non-zero. Okay, so very good. So with this, you can now compute the R dot Q. That is another vector. The 3 terms in the vector are these 3 terms. And so R hat is basically a vector. I have written it in this way. This is the I component, J component, and K component. So I've written it in this way. And you take the dot. You can just take the matrix multiplication here. Okay. And once you take the dot, so this simplifies, I think, to this expression. You can combine the cos and sine. Okay. Just check my algebra once if I have done this correctly. Okay. And then if we take the 3 time derivatives, then you see that essentially they the cos becomes sine and the sine becomes cos with sines, essentially. Okay, and also let us compute this other quantity where you have taken the 3 time derivatives and dotted with another r hat. So then that is not a vector anymore, that is a scalar, and this scalar has this form. Okay, this scalar has this form. Now in the magnetic field, this is the expression that appears, and we have to find the square of it. So if I write it out and try to simplify with the epsilon ijk symbols, we can show that it reduces to r hat, dot this object. The whole square means, you take the vector, this vector first, and then find its magnitude. Okay, and then this is a scalar square. Okay, so these 2 things we have evaluated before. This is a vector, and you have to find the magnitude of this vector, and this scalar you take and you just square it. Okay, and subtract it. Okay, so if you do that, then you get, it simplifies to this expression here. Okay, and if once you have this, then again, there's something interesting to note. If you're moving it with frequency omega, then angular frequency omega, then basically what appears in this harmonic thing is basically 2 omega. Okay, it's just a consequence of the algebra. This is something which is quite interesting. Okay, now if you take the time average of this quantity, then this is the angular dependence that you have. You can try to plot this angular dependence in a polar plot. If you take this thing as a, this thing is theta, so you can try to plot to get an idea of what are the directions that are along which the radiation is maximum. Okay, so right. So you can take this form, and so this is the angular dependence that goes into the power per unit solid angle, and that goes as omega to the 6, and this is the angular dependence. Okay, that is the result for this rotating quadrupole. Okay, so now you can compute the total average power, and it's basically a simple integral of d theta from minus 0 to pi, and that is given by this 8 by 5. Again, check if I've done this correctly. Okay, and then the omega to the power 6 dependence remains. Okay, so this is the final expression you have, and you see, this is the typical length scale A, and it goes as A to the 4. Okay, Q square is of course there. So just remember the dipole moment, that went as P square, P naught square, omega to the 4, right? So, so you see, it went as P naught square dipole. So for the dipole, just to re-emphasize that fact, for the dipole, this P went as P naught square omega to the 4, right? And as you can see, this P naught would have a typical, it will be like, Q d square, where this is the Q square d square, where this is the, d is the dimension of the dipole, right? Omega to the 4, okay? And of course, there are factors of C here. So you see, this one is off, off by powers of omega. This is the, this A is the dipole length. So, if you consider the typical length is L, so L is A here for the quadrupole, that is the sides of the square, and L is D for the dipole. Okay, so if you consider omega L by C, this dimensionless ratio, okay, if this is small, okay, implies that quadrupole radiation would be small. Okay, so if this is small, implies P quadrupole is small compared to P. P quadrupole is small compared to P dipole. Right. Sorry. Yeah, I'm just crossing the page here, so I'll just make it small. All right. So, yeah, just, this is the discussion that we had before about this length scale being small. Okay. So now, so more or less, this is the part that is there in your syllabus for your next exam in next week. Okay. So I hope that this is clear. The main takeaway message is that you have to be able to use the formulas that I derived and find, this the angular dependency of dp d omega, or this total integrated average power. These things you need to be able to compute. Given that I give you some kind of a oscillating quadrupole or dipole, you should be able to compute that. I will give you some more exercise in your problem sheet so that you have some practice with it, but I really want you to learn that exercise, okay? But apart from this, I'm going to finish our discussion now with, I'm going to add in, this discussion about radiation is really not complete without a discussion of the antenna, okay? But as far as your exam next week is concerned, there is no, that antenna discussion, or the antenna will not be a part of syllabus of that exam, okay? So, so this is like, a kind of a fun application of the ideas that we discussed. But, so, it's only up to this point that I want you to learn about radiation. So basically there are these three terms that we discussed. So of course there can be a situation where there's simultaneously electric radiation and magnetic radiation and electric dipole radiation, magnetic dipole radiation, electric quadrupole radiation. All of these things can happen simultaneously. So let's say in such a situation, you can ask that what happens to cross terms between electric and electric dipole and magnetic dipole terms, because we have E cross B, or in the power we have E square or B square. So there can be cross terms when you are computing these quantities. So if there are any cross terms that survive the time averaging, these cross terms will essentially be zero if you compute the total power. Okay, because of the different kind of angular dependencies, these cross terms will typically vanish if you have, the angular dependencies are such that these cross terms typically vanish for a given configuration. These cross terms typically vanish in the full in the full total integrated power, integrated average power. So you don't have to really worry about the cross terms. If you just compute the, if you treat them separately, the electric dipole radiation, magnetic dipole radiation, electric quadrupole radiation, and so on, if you treat them separately, that is like going to give you the full picture of what is happening, even in a complicated scenario where all kinds of radiations are happening. Okay, I hope that point is kind of important, and I hope that is clear. So, the cross terms don't contribute. The bottom line is that. Okay, cross terms don't contribute. So, very good. So, right. So now, so before I describe to you a very simple, so we are going to deal with a very simple model of an antenna, which I'll describe to you. Again, we are going to do it slightly, as a fun application rather than a very intensive thing. But before I do that, there's something very interesting and important which we can see, and this is called the radiation in frequency domain. If you have noticed so far, I have only talked about if we have a dipole or a quadrupole which are oscillating in a given frequency. Okay, so I have considered only monochromatic oscillations. Okay, so in real situations, the oscillations are not typically monochromatic, and they can have a combination of frequencies. Okay, in such a situation, it is often very useful to go and consider Fourier transform. Okay, to consider the Fourier transform of the fields, then it makes life and calculation much more easier to talk about things in the so-called frequency domain, or basically we are talking about things in the Fourier transform. We are talking about the Fourier transforms rather than the fields as functions of time. Okay, so that really helps a lot of the calculations if we consider the Fourier transform, where there are many frequencies present. Then the Fourier transform is a useful object to deal with, and because the time variation then can be very in terms, so when there are many frequencies present, the time as a function of time, it can be a very complicated function. So it may not be a harmonic in time. So but you can always take such complicated functions of time and Fourier decompose, and that will give you in terms of harmonic functions, you can decompose it, and then you can talk about the Fourier transform. Okay, so therefore, before going into the antenna, we can talk about a little bit of radiation fields in the frequency domain, or basically it's just the same thing that we discussed so far in the Fourier transform basis. So basically we know that the radiation that we have considered is produced by this term, okay, the 1 over r term in the vector field that we have seen, right? So now we can do a time Fourier transform of the current. Okay, this is the time Fourier transform of the current, and then we can also do a time Fourier transform of the vector potential. Okay, if we do this and plug it back into this formula, keeping only this leading order term, then we find the following, that this is the time Fourier transform. But now if we do the Fourier transform here, we see that we have to consider retarded time. Therefore, there are all these terms that are here. Okay, so because here there was retarded time, therefore this is not simply time here in the Fourier transform. Okay, so that therefore, if we simplify, then there is a e to the power I omega t, and if we just take the e to the power I omega this integral out from both sides, compare compare coefficients of e to the power I omega t in the Fourier sense, that they are independent functions. So for different omega, so therefore we can drop the integral and compare the coefficients only. So if we do that, then the Fourier transforms would be related in this way, where you will have these additional terms coming out of these different terms in the expansion of the retarded time. Okay, so if you have this, then you can pull this e to the power I omega r outside. So omega r is denoted by k, and so if we take this and denote omega, k equal to omega by c, in the r in the sense of like, you know, it's pointed along the r hat direction, then we can write this part as e to the power minus I k x vector in this way. And so basically, this is the is now the Fourier transform, and the x integral remains. Okay, it's Fourier transform only with respect to time. So the x integral remains, and but you see, this object that we have ended up here is basically now the Fourier transform with respect to x also, because this is e to the power minus I k dot r d cube x. So this is just the Fourier transform with respect to the x variable, and that I'm denoting by a tilde of j. So it is now a function of k and omega. If we take this and evaluate it, we'll get the Fourier transform of j. So in Fourier space, this becomes a simple integral without any, this becomes a simple expression without involving any integrals. So it's just e to the power I k r by r and j k of omega r. So you see, this r dependence is there. Okay, the r dependence is completely captured. The omega dependence is there in the k, and the omega dependence is there here as well. Okay, so that is how, you know, this statement is, this is like a partial Fourier transform, but this is like a full Fourier transform. Okay, that is the interesting part. Okay, so in this way we can do the integral over the space if we consider the Fourier transform. Okay, so very good. So once we do the Fourier transform and now try to compute the curl of A and we use the electric field, you know, the same drill that we did before. So the curl of A is going to give us, again, it's the same way in which the curl has operated on this quantity, but now the function explicitly exists. You know, this function explicitly exists. So you can just take this and find, you know, the r dependence is explicit, right? So you can take the curl. Again, the curl is not going to hit the denominator because it will give you a higher power. It will only hit this e to the power ikr. And if it hits the e to the power ikr, you'll get a ik r hat for the magnetic field. And the electric field similarly is going to give you another, you have to take another curl here. Okay, again, I'm considering only the 1 over r pieces. Therefore, basically you have to, you have to be a little careful. You know, there can be also, the curl can act on this 1 over r, but it doesn't matter. Like it will give you higher powers of r. So I'm throwing them away because I'm considering radiation fields. So basically this is the form of the radiation fields, the electric field and the magnetic field in terms of the radiation vector potential. Okay, this is direct, and in terms of now again, you know, the electric field and the magnetic field again has this form, which, you know, the radiation fields have this form. Okay, and then you can compute the pointing vector again. It is pointing again along the r hat direction, and it's like b square. So if you compute b square now, so now b square you can compute, and as you can see, the b square can be given by, you know, this expression square. Okay, but you can, you know, because we are using complex notation, you can do something which is very interesting for complex notation. So if you are given me this complex quantity, complex vector, let's say, okay, and if I'm interested in time averaging of the mods a square, okay, then what I can simply do is, instead of finding a dot a, I can find a dot a star and divide by half. So a dot a star gets rid of this quantity, and if I divide by half, then that is the half that comes from time averaging. Okay, so this is a procedure of taking the time averaging. Okay, so I can immediately do the time averaging if I agree to, instead of doing this dot this, if I take a star and put in a factor of half, I can do the time averaging immediately. Okay, so if I do that, then therefore my differential power in some, so the power in unit solid angle, power per unit solid angle is given by this factor of 2 here and b dot b star. Okay, this takes care of the time averaging. So if I take that and do this averaging here, so if I take the star and find the average, so I can just do it with this result here. Okay, because I have to take the star, so I becomes minus I, and that takes care of the sign. So it becomes omega square here. And now I have to find the magnitude of this vector. And this vector, as we know, the A is given in terms of the J that I found here, in terms of the Fourier transform of J. So this is entirely given in terms of the Fourier transform of J in this form here. Okay, so dp d omega is given in terms of the Fourier transform of J. So we see that the frequencies that are going to be present in the radiation are the frequencies that are present in the Fourier transform of the source, and basically on the transverse Fourier transform. Basically, you take the Fourier transform of the source and cross it with R. So basically this will be perpendicular to R hat. This is the direction of the propagation of the wave. So basically, if you take the transverse directions compared to R hat, this is called the transverse current. So if you take the transverse current and find what are the frequencies in the transverse current, then those are the frequencies that are going to be present in the emitted radiation. Okay, so this is a nice and cute formula with which you can work even when there are many frequencies. Okay, so this is like the different frequencies will contribute differently, and the frequencies that contribute would have this form. So again, so basically this is the contribution of a fixed frequency in a given direction, which is the power which is emitted in a given frequency in a given direction. So the way this guy is oscillating in any way it likes. So there are many frequencies. You fix a direction. So this is the dp d omega, and you ask that what is the power emitted in a particular frequency. Then the answer to that is given by this expression here. Okay, whatever are the frequencies present here, that will give you a non-zero contribution. Okay, and that also gives you the amount of power that is emitted in that given frequency. Right. So yeah, this is what I have written in words here. Right. So now we are in a position to discuss the most simplest form of an antenna. Okay, it's called the thin wire center-fed dipole antenna. Why thin wire? Because if the wire has some dimension, then there are complicated surface effects that one needs to discuss and talk about. But let's say that the radius of the wire, or this wire here, is like a if you say that in general this wire has a diameter, but we are going to consider when this diameter is extremely small. Okay, so we don't have to worry about any surface effect or any such thing, complicated currents on the surface, etc. So it's just a small thin wire, and we have the center of two directions like this, that is fed by a alternating current. Okay, this alternating voltage is given in this way. So if you put an alternating voltage here like this, then a stationary wave would be set up, or stationary current would be set up on the two branches of this wire. Okay, and that stationary current that would be set up has this expression. Of course, it inherits the harmonic dependence of the potential, but apart from that, it also has this stationary wave nature, which is this sine k. Again, this k is omega by c. This sine k d minus z by this sine k d minus z. Okay, so this d is this length here, and z is basically this z axis. Okay, so this is non-zero. Only z should be considered, because this current is non-zero only when z is greater than equal to minus d and less than equal to plus d. Okay, only in that case this is non-zero, and I is entirely a function of z. It doesn't have any xy dependence. So the xy are these axes, xy doesn't have any xy dependence. It's only a function of z, but also for not all z. Z is limited between minus d and plus d. Okay, that is the thing. And between minus d and plus d, there's a current that is set up, and that current is basically a kind of a standing wave current that is set up within this conductor. Okay, so this is one way to represent that standing wave current. And now the job is very simple. For this current, because it is fluctuating, what is the radiation that this guy produces? So this is let's say an antenna in broadcast mode. So this is going to broadcast some radiation. Okay, so let us see what kind of radiation does it broadcast. So we will see that right. So right. So it the kind of radiation that it will broadcast would depend very crucially on this frequency omega. Okay, we'll see why. Okay, so it's so basically we take this current, and if we take this current, then we know we can find the Fourier transform of this current, And if you want to find the Fourier transform of this current, as we know, current density to current, we just convert the volume integral into a line integral, and of course it is pointed along the z direction. You remember the mnemonic in magnetostatics, that's what I have used here, and I have written it in this form. Okay, so if we now take this and plug in the standing wave, this thing is given by this thing here. Okay, if you plug that in, then this is a complicated integral that we have to solve for integral over z. Okay, minus d to plus d. That is the only interval for which the current is non-zero. So that involves an integral of this form, and you can find, you can look up your tables or do it, yourself if you are brave enough, that this integral is given by this quantity here. Okay, and this quantity is now considered, you can just take it in and plug it in the respective values of a, b, and c from this integral, and then this integral can be evaluated. The Fourier transform is evaluated and it's found to be of this nature. Okay, it is of course along the z direction. Okay, because this original thing was along the z direction. Okay, so this Fourier transform is basically this object here, where there's a theta dependence, there's a d dependence, and there's a k dependence, and this k is basically omega by c, where this omega is the driving frequency of the voltage. Okay, so now again a rad is given in terms of this Fourier transform entirely, so it is given by this expression, and if you take that and square it to get, r cross this thing would give you this expression. Okay, I mean, I'm just doing the algebra here. So this is the integral has given me this, so I can take a r cross. This is going to give me an additional sine theta. This is going to give me an additional sine theta, and when I square it, it will become sine square theta, and whatever is there inside here, that will get squared. Okay, so that so now this is essentially the differential power. Plugging it back into the formula for the power per unit solid angle, this is the expression, and the theta dependence is quite non-trivial, as we see that the theta dependence is very, very non-trivial. It's a cos of a cos, or very complicated function. Okay, so in general, this dependence depends on the geometry of the antenna. We have considered a very simple, center-fed, linear center-fed antenna here, and this depends on the geometry. You can have more complicated geometries, and that would eventually, what kind of current, that would determine what this current form is, and that eventually would determine what this form of this radiated, radiation, how this power is radiated in various directions, that is going to be sensitive to the geometry of the antenna. Okay, so very good. Now, given this differential power, we can ask that, what is this differential power we see? So you see, here there's a very interesting thing going on. It depends on how the wavelength, so the wavelength is defined in terms of the frequency, which is basically the driving frequency. Okay, so given that we are driving the antenna with some particular frequency, that will determine the corresponding wavelength of the radiation, and if that wavelength is comparable with this d, you remember this d was basically the length of the antenna here, right? Right. So this is basically the length of the antenna. Okay. So if it is some multiple of this d in this fashion, okay, then depending on what multiple it is, the direction of this directional dependence is different. Okay, that this directional dependence is different, and therefore basically we can use this. So again, it depends on what So for I have plotted this function for m equal to 0, 1, and 2. And as you can see, the plots are such, I've just taken this and plotted it. You can take it and plot it in any software that we know. I plotted it in Mathematica. And you can see, I've done this polar plot. So this is like a function of theta. Okay, this is the theta angle. Okay, by the way, this is my z-axis. Okay, when I did the plots, it got like inverted. So this is my z-axis, and this is the theta with which I'm plotting. So you'll see that, different directions get maximum value depending on what this, how the wavelength compares with the dimension of the antenna. Okay, so now you can take different frequencies and you can superpose them, and that would be emitted in the radiation, and that radiation would be of this form, it will be radiated in this particular way in various directions. Okay, and of course you can modulate your signal using different frequencies, and that would be sent out as a broadcasted signal from a given antenna. Okay, now it so happens that antennas are this is the emission profile. So the emission profile of the antenna, or the emission profile of the antenna, is pretty much the so the angular distribution of the power radiated when an antenna is operating in the broadcast mode is pretty much the same angular distribution as when the power is absorbed. Okay, so the angular distribution of the antenna, if you now want to absorb radiation, if you orient the antenna along this direction, okay, orient the antenna meaning what? Like if I put the z-axis such that, let me see, what do I mean? So basically the absorption happen when, so if I orient my z-axis along this direction, then maximum absorption will be happening in this direction. Okay, so if I turn the problem around, let's say my radiation is coming from this direction. Let's say this is some broadcast signal here. Okay, now if I orient my z-axis of the antenna in this direction, then my absorption will be maximum, because it is the same sense in which my emission would be maximum if I am driving the antenna with the center fed potential. Okay, so in this way, both the angular dependence of absorption and emission of the antenna, that is the same. Again, the antenna geometries are very complicated, and basically the geometries of the antenna are designed so that the signal that is produced has, let's say, the desired directions, etc. Okay, so for instance, like I've discussed only one antenna, like one of this thin wire antenna. So you can put in like many you can put in a grid of this thin wire antenna and make the signal almost like all the power focused at a given angle. Okay, that is also possible. Okay, so I think Zangwill has a very this discussion is taken from the book by Zangwill. So that has a very interesting and more detailed discussion with the antennas. So you can try to look at that discussion a little bit if you are interested. Okay, so this is all that I have to say about the antenna. And the last thing, this I mentioned before. So the antenna is radiating out, and so this is, as you can see, is also proportional to I naught square. So now if I define so the total power, total power, P I can define by integrating over theta and phi. And that, if I say, is equal to half R radiation I naught square, then this is the radiation resistance that I have to overcome if I want to send out a signal. Okay, so I have to supply that amount of energy to the antenna and feed it via this potential that I'm feeding the center of the antenna, and that energy would be radiated and sent away as radiation far away. So I hope the idea is more or less clear. You have to do a lot of exercises to get in terms with this idea. I know this is new to a lot of you, but let me terminate the discussion here. And so in the next video, I will try to focus on a single point particle. That is a very important and curious example. And I will try to understand how radiation happens from a single point particle. Okay, just to give you a prelude, so we have already seen here that, in the Larmor formula, in that little bit of discussion we had seen that it is proportional to the acceleration square. Okay, so we are going to see that how that happens in general. Okay, in general, the electric fields, how that can depend on acceleration, and how the Larmor formula comes around from a very generic description of the point particle and considering its retarded potential, that we'll see in the next video. So, okay, thanks a lot for your attention. Let me terminate the video here.